All right. In this example, we're going to look at some more exponential growth and decay type of situation here. Real life-ish, kind of, if you died 5,700 years ago, real life. So scientists are using carbon-14 dating, which uses 5,700 years for its half-life. Find the age of a sample in which 10% of the carbon originally present has decayed. So the formula that we're going to stick with is the one that we've kind of been using, which is let's see here, y equals that initial amount. And in this case, we're talking about half-life. So our base is going to be B. And if 57 years is half-life, that means after we go 5,700 years, we will have lost half. So for our exponent up here, we're going to talk about T over 5,700. Okay, and T would be the number of years. So this is the setup for this particular guy. Well, scientists are going to use carbon-14 dating. All right, we've got all that, 5,700 years, got that. Find the average age of a sample in which 10% of the carbon originally present has decayed. Okay, 10% has decayed. So basically what we're saying here is 10% of our original amount is left. So we've got 0.90 or 90% of our original amount left. Okay, that's how this problem is going to set up. So we're going to substitute all of these things in here, where you're going to have 0.90 times our initial amount is equal to our initial amount times 1/2 to the T over 5,700 power. Okay, not hard, not hard. Now, solve this guy out like you would an algebra problem, and the first thing that we want to do is kind of clear off all the things that are on both sides together. So I can actually divide by the initial amount, and looky here, the initial amount actually cancels out on both sides. So as it turns out, he's not important when we're trying to solve for T in this situation. And the reason is because we're looking at a percent of the original amount left over. Okay, if we had a different Y, then this wouldn't work, okay? But since we're talking about the initial amount the whole time, that's not a problem. So 0.90 equals 1/2 T over 5,700. Okay, now take the natural log of both sides, okay? So the natural log of 0.9 is equal to the natural log of 1/2 to the T over 5,700 power. And when you do this, anytime you have an exponent inside a natural log, anytime you have an exponent inside a natural log, you could take that exponent and move it to the front of the natural log. So natural log of 0.90 is equal to T over 5,700 times the natural log of 1/2. Okay, and again, we're trying to get the T all by itself here. So we would multiply both sides by that 5,700. And then we would have this. So we would have 5,700 times the natural log of 0.90 equals T times the natural log of 1/2. So I can finish this then by dividing both sides by natural log of 1/2. And when I do that, I get the age of a sample in which only 10% of our carbon has decayed. So let me just punch that into my calculator real quick. And what I get is 5,700 times natural log 0.9 divided by natural log 1/2. I get 866.418 years. So that's about how long it would take this 1/2 to work. And this problem isn't really too bad, and it's actually, the part that we're dealing with isn't too calculus-y. This is almost like a rewind of pre-calculus and really manipulating your logarithm rules and working with those. The trick here, though, is dealing with that initial amount. It cancels out. It doesn't always. And so just because we do that this time doesn't mean we do it every time. However, when you're dealing with original amounts and percents of original amounts, in the end, you don't need to know that because that's what we're trying. It just cancels out. It goes away algebraically. Okay? So there you go. Carbon-14 dating.